right, now we are going to solve a similar force problem that's slightly tweaked. We are going to solve a force problem that is situated on what's called an inclined plane. So this is one common type of problem that you'll experience in your physics class and other relatable physics classes. So first of all, we've got our block that says it's resting on an inclined plane. So the first thing I want to do is visualize, all right, inclined plane, what does that mean? So we're going to have some sort of a thing that looks like a hill. I'm going to draw that. I'm going to draw an inclined plane. Looks like that. So it means I can sit a block up here that's on this some sort of this angled surface. Okay. So this diagramming thing is very important here. That first step is going to be very helpful. So a block of mass is resting on an inclined plane. It makes an angle of 30 degrees relative to the horizontal. So I know just how steep this hill is. Solve for the coefficient of static friction if the block is just about to slide down the plane. So imagine taking something on a book and then raising up that book until the object starts to slide. That's kind of what we're doing here. So we've already achieved that spot is when this inclined plane reaches 30 degrees. So whatever roughness that this block has, whatever roughness is between those two materials, it happens to start sliding right when we reach the 30-degree angle. It's a little bit lower, maybe it wouldn't start to slide, okay? So we have our diagram set up. Now we can do a free body diagram, which is probably going to be the more important step with showing how we tweak this slightly to solve for an inclined plane. So now that we have a diagram for the inclined plane problem, we can start with the second step, which is still going to be the same for our problem solving process. We're going to try to draw a free body diagram for our object in question. Now in this part, if we isolate this box as our object, I'm going to draw it just like it is here because my box is not just sitting flat like normally things would be, but it's tilted. So I'm going to draw it tilted because I'm thinking that's going to be a little helpful later. So if I draw a little box, and notice I tried to tilt it versus drawing it flat up and down. And I'm going to represent all of the forces that are currently acting on the block. We always start with gravity, so we can draw gravity. Now, gravity doesn't change its direction just because we have something sitting on a hill. It's still going to push straight down towards the center of the earth. So I'm still going to draw that arrow. Gravity's pushing straight down on this block. So I'm still going to draw it in that direction. And we'll call that mg, just like we did before. Okay. Then if I look at anything else in the block, I know that there's a plane here that it's sitting on. So just like before where the ground was pushing up, we have our inclined plane, but it's kind of pushing sideways a little bit. So if you think about what a normal force really means, it got its name because it's named after a normal line, which means that it's going to be perpendicular. So the normal line will be perpendicular to our surface. So if our surface is facing that way, then our normal line is basically going to go right outside of that surface, perpendicularly. So I'm going to try to draw that up in that direction. It's kind of at an angle. And again, that's if you want to draw it right on your picture too, you can be kind of straight up in that upward direction there. Okay, so we've got our normal. Now, if we look at anything else, so I know that the block is at rest, but yet it looks like it can kind of slide down the hill. So how is it that it can be at rest? Well, that's where friction comes into play. So it says in the problem we're eventually going to be solving for the static coefficient of friction. So I'm thinking that that's where this is going to come in. If there was no friction here, then this would just slide down the hill because gravity is going to kind of push it in that direction. So if I think about it, if we don't want to slide down the hill, friction is going to oppose that and we'll push that straight up. So I'll draw it I'm going to try to draw it parallel with that surface. So I'm going to draw just a little dotted line here to help me represent where my surface is. Okay. And then I'm going to draw that static friction in that direction. All right. And if I look at our box, I don't have anything else that's in contact with the box. So it looks like we finished our free body diagram. So now comes the third step to our problem solving process, which was where we defined our coordinate system before. Oftentimes we are very used to that typical 2D coordinate system where you have X in the horizontal direction and Y in the vertical direction. But in a problem like this, where you have an object that's at an angle, that may not be useful. In fact, it isn't very useful when you go to solve things if you're trying to get to anything involving Newton's second law of motion and acceleration. So we do a little trick, which is called tilting our axis. I'm going to show you how that works. So if we look at this object here, our old axis was to say, all right, well, we have our, positive x direction going to the right, negative to the left, and then we'd have our y-axis perpendicular to that, okay? But if we look at this object, this box, regardless of what happens to it, if we push on it or pull on it, it's probably not going to go straight up. It's probably not going to go straight to the left or straight to the right. It's probably going to remain on this incline in some fashion. In our case, it's stuck there at rest, but if maybe there was less friction, it could slide down, or maybe someone could push it up the incline. But the point is with a problem like this, your acceleration is probably not going to be tied to this perfect left and right idea. So what I'm going to do is turn this axis sideways to where our acceleration is in line with the possible motion of the object. And that'll help us get things into a little more organized fashion. So we don't end up with a goofy acceleration vector. Pretty tricky to solve. So I'm going to draw my coordinate system right on top of this picture just so I remember this. And we've got, so I'm going to tilt it where our potential acceleration could be, which would be right along the actual inclined plane itself. So right along that plane, we'll make this our x-axis. And then y-axis is always perpendicular to that. So perfectly perpendicular, I'm going to make that my y-axis. So what you can see here, and again, that's just to emphasize that's perpendicular, you can see that it's still an xy axis. We've just tilted it sideways. And that'll be more useful in helping us solve this next part of the problem. So now that we have our coordinate system decided, we can start that fourth step, which was setting up those net force equations in the x and y direction. So we have our, I'm just going to set up a little place for them. We'll talk about those separately. So we'll have the sum of our x direction forces, and we'll have the sum of our y direction forces. Okay. So looking at everything in the x direction, and we've decided that our x direction really means parallel to the inclined plane. That's what we're really calling our x direction, or along the inclined plane if you'd like to think about it that way. And if I look here, I've got definitely static friction going upward along the inclined plane, perfectly in that direction. Okay, so I'll just say Fs for static friction. And then I don't see any other arrows that are pointed perfectly up parallel to the inclined plane or perfectly down. But be careful with this. Because if we think about our axis, anything that's going to fall in this x and y direction is going to fall directly on these axes that we've chosen. Take a look at gravity. Is gravity along the x or the y axis? And hopefully you have decided that it's kind of both. It's not just in the x direction, but it's not just in the y direction. It's in this coordinate over here. It's pushing straight down from the block in that area. So it kind of works in the x direction and it kind of works in the y direction. Gravity has two responsibilities. It wants to push the object down the hill, but it also wants to keep it attached to the hill. It's kind of got two roles here. So if I look at this in terms of vector components, this is where it gets a little bit tricky. I know that my force is mg, and I want to know how much of that force really contributes in the x direction and in the y direction. So we draw this little, I call it the gravity component triangle, okay? And it represents what the component vectors are for this particular force. Helps us put things in the x and y direction. So if I think about gravity going downward in that direction, I know that some of it sort of has to go down straight in that y direction, but some of it also has to push down the inclined plane that way. So you end up getting kind of this little triangle here. If I just draw a little triangle. So here's our original downward force. We get this little right triangle. And if you do a little bit of geometry, a little bit of fun with geometry proofs, it turns out that the angle of this incline here associated with that horizontal, this 30-degree angle, is the exact same angle that's up here. So that's also 30 degrees. And be careful with that. If you're given If this was a hill and you're given this top angle here, then you can't just substitute that in, okay? So again, do a little bit of geometry and you can verify to yourself that this 30 degree angle here with the flat surface, by the time you get done drawing perpendicular lines and components, this angle in here is also 30 degrees. So this gives us component vectors to use for our gravity triangle. So we've got, I'll draw them into my free body diagram. Part of gravity, I'll call that mgy, because it's going in our assigned y direction. And then the other part goes, it's really moving that way, it finishes off that triangle. But I'm going to draw it up here, because I know that that's what's really pushing the object in that direction. So you can draw this arrow, instead of having it down at the bottom, you can also draw it up here. So I know I'm going to have that mgx component. So that helps us put a little more detail into our free body diagram. If we think about what mgx and what mgy really are, if I look at this angle here, I see that our right angle is in this corner. And if I specifically want to know what this vertical side is, mgy, I can see that this side is adjacent to the 30 degree angle, and the gravitational force mg is opposite to that right angle. So that tells us that that's our hypotenuse. Okay, so if you think about adjacent side, opposite side versus the hypotenuse, that ends up giving us the common relationship, which you can save these if you would like to. mgy is adjacent to the angle, so that's going to be related to cosine. So that's going to be mg cosine theta. And then that opposite side here, that's where your mgx comes from. That opposite side, opposite to the angle, that's associated with sine. So we know that mgx is going to be mg sine theta. Now we've written our gravitational force a little bit differently so we can use it in our equations. So I'm going to apply those at this time. So now we can start representing our individual forces into our equation. This is where we've got to pick a positive and a negative here. We haven't really decided which way we want to call positive x and which way we want to call negative x. Same thing with y. If we read our question here, it was a little easier in some of the previous problems where we had an acceleration. Because it was like, okay, well, the object's moving to the right, so let's just make to the right positive. But in this problem, it's a little different. Our object is not moving here. So you can actually make a choice. Most of the time, we usually think of friction as going in the negative direction. So in this case, it might be beneficial for us to make positive down the incline and then negative up the incline. So it might be beneficial to do that. As long as you're consistent, that's what we want to look for. So I'm going to restart this, looking at what's specifically positive and what's specifically negative. So starting with our x direction. We drew this out earlier, and just to be clear here, these aren't three separate forces. But what we have done is we've rewritten the gravitational force to be a little more helpful to us. We've rewritten it in the x direction and rewritten it in the y direction to go with our chosen coordinate system. So if I look at things that are down the inclined plane, that's that x component of gravity that we drew that's pushing, that wants to push the box down the hill. So that's this mgx, which we define with some geometry as mg sine theta. So that's one of our x direction forces. Then I know that my static friction is resisting that, which is why it can stay at rest. And that's going up the incline. So that's going against that. So I'm going to use a negative force minus static friction. And in the previous problem, we set this equal to max. However, since our block is at rest, we can say that this is 0, since it's not actually moving. All right, for the y direction forces, now I want to look at everything that's perpendicular to the inclined plane. So I can very easily see that the normal force is pushing perpendicularly outward. We can call that upwards direction, up and out, the positive y direction. So we'll say normal force, that's one of our y direction forces. And then I'm looking for anything in the opposite direction, which is why we drew out this, again, component here, y component of gravity. that's opposing the normal force. We define this particular side as mg cosine theta. Okay. And then if we look at anything else drawn along that vertical axis, or a tilted vertical axis, I should say, and there's no other forces that are there. So we can set this equal to MAY, but we've established also that the box is not jumping off of the hill or sinking down into the hill. No motion, so both of these are 0. So these make these a little bit easier to solve with. And I'll do a little more algebra in our next step. So now we can start seeing if we can do that step 5 thing, where we plug in extra helpful equations if they're useful, and we can start looking at some numbers as well if we have them. So out of our story here, we're not given the mass of the block. It says the block of a mass m is sitting there at rest, but it doesn't really tell us what the mass is. We know g is a number. We could eventually put a number there. We know theta, so that's good to know. And static friction, again, we don't really have an exact number for that given to us, so that's where your variable form equation could be useful here. So we know that the force of static friction in this case, since it's at that place where it's just able to slide, it's just about to slide, we know that the static friction will be equal to the coefficient of static friction at that moment times the normal force. So we can put that little miniature equation into here and use that for solving. Normal force I don't know much about. Theta I know. So it looks like we don't have a lot of given numbers here. So I'm hoping that algebraically this thing is going to simplify for us. So let's see if I can work on this a little bit. So we've got two equations that are both equal to 0. One of them has this friction coefficient in there. So I know that these guys are going to be related to each other because they have to equal out to cancel out those forces, so this thing doesn't move. Same thing for the x direction. So I can rewrite my y direction force. I can say that not n minus mg cosine theta equals 0, but I can say specifically that the normal force is equal to that y component of gravity. And in our problem, it's mg cosine 30. It's basically just rewriting this y direction equation. I'm going to try something similar with this x direction. I'm going to move this negative friction to the other side of the equation. So that's going to tell me that mg sine theta, that x component of gravity going down the incline, is equal to that static friction, which is mu s times n. And now I've got two equations here. And if we look at those two equations for a second, you'll see that the variables are all very similar. In fact, we already said our theta was 30, so I can go ahead and add that in. That's our one known number. They both have m, they both have g, they both have to do with the angle of 30, and they both have normal force in them. So this is where you can start doing some algebraic substitution. If you know that your normal force is equal to mg cosine of 30, you can substitute that into here. So you get mg sine of 30 is equal to your coefficient times your normal force, which in our problem is mg cosine of 30. And we know with algebra, when you've got everything multiplied, same stuff on both sides, we can cancel out our m, and we can actually cancel out g, even though we know it. So those algebraically cancel out. So it turns out we didn't even need the mass. So don't freak out if you're not given a number. You might not even need it in the long run. And I'm looking for this unknown here. So I've got to do some algebra. I've got sine on the left side, mu times the cosine. So I'm going to divide by that other stuff. So I'm going to divide by cosine of 30. And then we've got our coefficient left over. And if you think back to trigonometry review, what is sine over cosine? And hopefully you remember that that's tangent. So it turns out in our problem here that the coefficient of friction is just the tangent of 30.